before we get into the actual methodology, let's talk about what is least cost scheduling. In a project, like you can concise it to some degree based on some time variation or change of time in particular activity, so that you can accomplish the task early. So that is what we can achieve. But when you reduce duration, for example, if an activity requires 5 days and requires 5 people, but you can finish that by 2 days or 2.5 days by employing additional people. So that is how, by reducing, it doesn't mean that it is cheaper. It incur more cost. So that's what we're gonna do. We're gonna find an optimum time and optimum cost. So the steps we'll be discussing with the flow of our presentation, and this is a typical example that we have considered from the beginning for the CPM and PERT methodology. But in this case, it's a little different when you compare to the previous methodology. The reason is that in this case, the duration itself is 2 and cost itself is 2. So the duration, the normal duration is the actual duration put forward, but crash duration is if a client requires or you want to complete that within the quicker duration or something like that, then that is called crash duration. So you can see that the normal durations are always a little higher when compared to the crash duration, which means that we are reducing the normal duration to some degree based on the requirement. And so is the cost. Cost, the normal cost is the actual cost, whereas the uh, crash cost is the corresponding cost for crashing the activity. Say for example, to crash 4 days to 2 days, you have to incur 790 rupees, whereas the actual cost for no, making that activity is for 4 days is 720 rupees. So which means that the crash cost is higher when compared to the normal cost. So which means that you have to incur additional manpower, additional resources, so that the crash cost is always higher. And this is the total normal duration and total crash duration and total normal cost and total crash cost and something like that. And a very interesting factor to be note down is overhead cost. Overhead cost is an extra setup charge or something like that in addition to the normal charges. So they are generally calculated separately without the activity cost. This is all activity cost, and overhead cost you can call it as a contingency or site expenditure, or maintaining some facility or something like that. So that is what we call it a overhead cost, and this is generally calculated per day, and this is 100 rupees per day, right? Something like that. This is very interesting, and this is our typical network diagram. So we have replicated this concept from the critical path method itself. So we have taken the same diagram, and the normal duration is from the critical path network itself, so that we can find easily the critical path, the duration of the critical path, and so on. And within the bracket, remember, in a critical path method we have only one time, but in a PERT we have, even though we have got 3 time, we'll find equivalent time. But in this case, there are two different types of times. One is the activity, the crash duration and the normal duration. Crash durations are generally smaller and they are written within the brackets. Say within this brackets, 2 is the normal duration, 1 is the crash duration. So this gives us an evidence like how we can proceed further or something like that. And so is the cost. The normal costs are given outside and crash costs are given within the bracket. So this is the time schedule and this is the cost schedule. And from previous example or from a critical path method lecture, we know that the critical path is 1, 2, 3, 6, 4, 7, 9, 10, and the critical activities are A, B, G, H, I, O, Q, and the total path duration, critical path duration is 33, which is the project duration as well. So we can even calculate using the shortcut thing, but this is only permitted for this methodology, crashing methodology. For CPM, you have to find earliest activity time and latest activity time, and earliest event occurrence time and latest event occurrence time, and find the total buffer or total slack. Then which are having a 0 or no slack, then that will be critical activities. So you have to formulate that way. But for this thing, even least cost scheduling is a very iterative process. So it'll be good if you find out like what is the critical path, the longest path in the network diagram by this methodology. In this method, as I told you, the longest path is this A, B, G, H, I, O, Q, and the path duration is 33, right? And this is a normal critical path, normal duration critical path. So you have to find out how we can crash it to a greater degree. So this is a very important thing. So the total project duration or the critical path duration is 33 days, right? So this is a very important thing. And the total cost equals to direct cost, which is total normal cost, by adding all these things. Total cost is total direct cost. Direct cost is all the same, 360, 720 up until 136, and the total direct cost is 10,559. Right? So 10,559. Then overhead charges. We know that project duration is 33. 33 into 100. So per day, the project duration occurs, the overhead charge per day is 100. So for 33 days, which is the actual project duration, which means 33 multiplied by 100 will be 3,300. And direct cost plus overhead cost is the total cost. So total cost or total normal cost equals to 13,859. So which is inclusive of direct cost plus overhead charges. Next is very important thing. Kindly make a note of this. The difference of cost, which is crash cost minus normal cost. The reason is that crash cost is higher than the normal cost, so which means we'll minus normal cost from the crash cost. Then change in time or the difference in time, which is the normal time minus crash time, which means the normal time is higher minus the crash time. Or you can even take an absolute value of this, so that will be very useful in finding the cost slope. So let's define what's cost slope, which is the change in cost divided by change in time. So which means that crash cost minus normal cost divided by normal time minus crash time. So this is typically a slope, cost slope. So this will be very useful in our methodology, least cost scheduling methodology. So I repeat, cost slope is the change in cost divided by change in duration or change in time. Crash cost minus normal cost divided by normal time minus crash time. And here is the typical calculation for each activity, activity A to Q. The normal cost is given from the table and the crash cost is given. So we'll find the the difference is the absolute difference. So it is not 360 minus 417, but it's absolute difference between all the activities. And finally, total normal cost is 10,599 and the total crash cost is 2,420. And this is a very typical example. And if you calculate by the, why we need to find total is that to check whether you have incorporated all the activities and the corresponding normal cost versus and also the crash cost. And so as a time, so you take time and normal time and crash time and you find the absolute difference, so that will become the normal time and crash time, normal time minus the crash time. And finally the change in cost divided by change in time, so that will be our cost slope. So this is a very interesting metrics for least cost scheduling. Let me define that in the couple of slides later, but understand that cost slope is the change in cost divided by change in time. So this is the table. Generally this is the table will be very useful for determining the least cost scheduling methodology. Generally, people used to do, if you have done an operation research, people used to do it in a network diagram itself, but that would be very difficult to interpret and will be clumsy. So this table will be of, very useful when you do it in examination. It will be very handy and something like that. So this is an elaborative table. First will be the activity, then the duration, normal and crash, then cost in normal cost and crash cost, then the difference in cost and difference in duration, and then the cost slope, cost change in cost divided by change in time or change in day here, So that will be here, right? This is the left hand side, and all arbitral distance. It will be a trial and error, so you can keep on increasing the number of columns. So that will be very useful when you do this kind of a large computation. And this is very important. In the initial stage, there is not any reduction in the day. The project duration is 33. So our objective is to reduce the project duration such a way that at one point it will become an optimum value, and that point will be our optimum cost, and corresponding time will be optimal time. And increased cost per day, so there's no increased cost per day, which is there's no penalty at the initial moment. And direct cost is from the total normal cost, and overhead cost is 3,300, and this is anticipated for 33 days. If you reduce it, and this value is going to be reducing, so we'll take a look at that. And initially the total cost is 13,859, right? And not all these factors can contribute, so I've just shortened this table further. Let's take a look at that. So this is the normal duration, normal critical path duration, and crash critical path duration. Yeah, this is how I've shortened the table. I don't require everything. I only require change in days and the cost slope. So activity, change in days, and cost slope, and day shorten. So this is what my interest is. Then I highlight, no, since it's a computerized thing, I have highlighted in red color, but you can provide some symbols like asterisk symbols to denote A, B, G, H, I, O, and Q, or crash, I mean not crash, critical activity, right? So among this critical activity, the rest is the same. The table is the same. Only thing is we have shortened that, so we don't require the other components. We only need activity, the change in day, and the cost load, right? And highlight the critical path. You can especially use pencil for this, because we'll be using we will be iterating this to a greater degree. So use pencil so that the critical path get changes, alters. Then we have to find the least cost slope. So among the critical paths, the first step is to find out the least cost slope. So which means that among the critical activity, we have to find out the least cost slope. So which means that, so if I take a huge cost slope is nothing but the increased value. Say for example, because of your reduction of one day, what is the additional charges could happen. So you cannot, in a basic CPM methodology, there is a concept that you cannot reduce the critical path. The reason is that it does not have any buffer, and it does not have any additional resources, something like that. But in this methodology, we have additional resources by in the means of crash cost. So we have extra money so that we can reduce it to one day. But how much money we spend it for reducing one day is the cost slope. So if you take it a higher cost slope, then it's not valid, because it is not necessary to provide job that have a higher cost slope. But you can provide, initially you can exhaust all the least cost slope, then you can go with the higher cost slope, then it's logical. But when you start with a higher cost slope itself, is then it's not correct, something like that. Same way, in this case, A, B, G, H, I, O, Q, among this, which has the least cost slope? So the least cost slope is 19, and that corresponds to activity O, and that can be reduced to 5 days. So this is a very interesting thing. So let's take a look. First, we will circle the least cost slope. So make use of your pencil to do this in examination, so that you can erase this, because cost slope gets varied, the critical path also gets varied. So let's take a look at that. In this case, the least cost slope is 90, and it can reduce up to 5 days. This type of algorithm is called reduce a day algorithm. So which means that we will be reducing, no matter we have 5 days, we will be reducing one day only at a time, and see the implications. Say for example, if I reduce it to 1 day, and this 33 becomes 32, right? And the cost slope, which is the additional incur cost, will be 19 rupees or something like that per day. So which means that 19 rupees can I increase? So which means that direct cost, which is the total normal cost, will have an additional cost of 19 rupee. And the overhead charges, so overhead charges we might have saving because we don't have 33 days anymore, we only have 32 days. So which means 32 into 100 will become 3200. But when you add both the things, 10,578 plus 3,200, that will become total cost. So that will become 13,778. So which means there's a decline in the total cost. Same way, let's take a look at the CPM. The O activity, it's no more a 9 day, it become an 8 day. The reason is that we have reduced 1 day out of the 5 possible reduction, right? Then we'll check the critical path and we'll see that it's 32, still 32. And in examination, you don't have to draw multiple tables. You can draw tables and you can slash it. Like 33 now becomes 32. And the critical path duration does not change actually, right? Next, we'll see if there any other change in the, if we have not exhausted this. So we'll reduce 1 day. Then this will become 2 days, which means that 33 minus 2 will become 31, and the same cost loop occurs here, and then we'll add 10,578 plus 19 will become 10,597, and in this case is 31, so which means 31 into 100 will become 3,100, and when you add both it is 13,697. Then we'll take a look at it, and it's no more 8 day the activity O, it will become 7 day. Then the path duration 33 has become 32, and now it has become 31, and you see there is no change in the critical path duration. Then we'll continue the process. Say in this example, even despite changing 5, I've exhausted all the 5, and when we exhausted all the 5, and even though we'll check the maximum possible reduction is 4 for activity O. Let's take a look at this thing. For activity O, the normal duration is 9 and the crash duration is 4. The difference is 5. So we have reduced all that differences, and finally we got all those things and exhausted, and this will become 4, the maximum crash duration. So we cannot crash further or something like that. And this still this is the critical path, and there is no change. But if you reduce this to some 4 days, then this 24 becomes equivalent. Then there will be multiple critical paths. But the logic is that when you reduce an activity here A, and this also have activity A, so this also gets reduced equivalently or simultaneously. So let's take a look at the case where we get both critical paths or many critical paths or something like that. Then I've just completely exhausted this. Then we need to find the critical activities and which has the least cost flow. So when you take it 57, 35, 55, 48, 99, 19, 61. Among this 35 is the least cost slope. So which means that, and B can reduce it to 2 days further. So after this 5, you have to take this particular column. So you cannot do here itself, right? So after this, so I reduce 1 day. So this will become 6 days so far. 5 plus 1 is 6, and 6 and 33 minus 6 is 27. And remember the cost slope here is not 19, it is 35. So put the cost slope here, and normal cost, direct cost in the previous set plus the current increased cost per day, that will become direct cost. Then 27 into 100 will become 2,700. When you add both the things, it will become 13,389. Then we'll take a look at the chart, and it's still the critical part. Then we can do one more reduction in B, and after this B is not possible. So we reduce it and the procedure follows the same. Then we see, and still the critical path is the same. And we probably take a look at the other thing, which is the least cost slope is 48, that is H, and that can be reduced to 2. So we'll reduce it to 2 and see there's no critical path. You see, this is 25 and this is 24. So it's almost kind of an equivalent stuff. So we check that, and finally, you see, in this case, it becomes both critical paths, 24 and 24. So which means that we have got a multiple critical paths. So here is the trick. The trick is that it's not a trick, it's actual procedure. So which means that we have to consider all the activities of critical path. In this case, we only consider the one critical path activity. Here we have two critical paths, so which means the new critical activities will be D, F, then IOQ is already here. So D and F will come into picture. So D and F will come into picture. Then while selecting the least cost slope, you should consider all the other parameters, all the other critical activities also. So in this case, F has got 25 duration and that can be reduced to 1 day. So when you reduce F to 1 day, and that path will become no more a critical. Say that's a trick in this. So when I reduce it F to 1 day, and that will not become any more critical. So we go back to the original critical path, ABGHIOQ. So ABGHIOQ. Then we will see which has the least cost slope. So we have exhausted H, so G will be, we have exhausted H, D and O, so we will have only G. So G can be reduced to 1 day, so 55. So when you reduce it, so I just shrunken that, then it can be reduced to 1 day and that will incur 55. Then when you reduce it, you will get both critical paths. So this will keep on happening until you have this particular graph. Actually, this portion I've calculated up to this thing. After this, you can try this and you can appreciate this thing, because it's a very lengthy